In this video, I'll be introducing the fundamental group and the induced homomorphisms that go along with it. So in the last video, we introduced the idea of a concatenation operation, where you could take any two paths and you could conjoin them together into one path. But there's a problem with that operation that doesn't make it nice for algebra, which is that it restricts what paths you can do it on. They have to specifically be paths where you go from some point to another one, and then you go from that same point to another one. What that means is that you can't reverse it, because you'd have a path going from x1 to x2. You can't conjoin that with a path going from x0 to x1. This is an operation that restricts what two inputs it can have. But there is a way to fix this. What you do is you take a single point and have the path start and end at it. This allows you to basically just ignore wherever it starts and ends, and just allows you to look at the structure of the path itself. Any two paths that start and end at the same point are able to be concatenated and in the other order. Because, I could do this one and then do that one, or I could do that one and then do this one. It doesn't matter. You can do it in either order. And that's much, much nicer for algebra. And so that is why we're going to be looking at a restriction of the space of paths to just the loop space. The loop space is going to be written as omega of x at some base point x0. And it's going to be the collection of paths f from x0 to x0. So from that base point to itself. Now, something you should note is that these loops can also be viewed as maps, which are from the circle into the space, where you have it that f of 1 is your base point. Basically meaning you have your circle, you have your point 1 right there, if this is the complex unit circle, and then you just map it into your space x. And you send 1 to x0, you do whatever you want out here, but you have to come back because it's a circle, and this is a continuous map. And so you just have a different way to look at loops that will become very important in the future. Now you might remember that we actually didn't just look at the loops, we actually looked at their homotopy classes, because that way you could have inverses and identities and associative properties. And so if we're wanting to find out a group, we're going to want to have those properties. And so when we're actually defining the fundamental group, we're not going to look at just the loop space. We're going to look at the loop space where those loops are equivalence classes of loops. Homotopy equivalence classes. Basically meaning we will do the loop space and quotient out by the equivalence relation, the path homotopy equivalence relation. And then once we do that, we understand that the operation, the concatenation operation, is a group operation. Because as we saw last time, it had an identity, it had inverses, and it had the associative property. And now that we're doing loops, it doesn't matter the order or the starting and ending points, because we know what they are and it can go in any order. And that's what we want for a group. So, definition 2. So the fundamental group we write as pi 1 of the space at a base point x0. What it's going to be, the underlying set is going to be the loop space, and you mod out by the equivalence, the path homotopy equivalence relation. Basically meaning this is the set of homotopy classes of loops. And then we can have the concatenation operation right there. The fundamental group is the space of homotopy equivalence relations of loops at a point under the concatenation operation. And by last video, we know that this satisfies the group properties. So what's some examples of calculating this? Well, we've seen in previous videos that if the topological space X is the real numbers, or Rn, and you do it at any point, we know that by the line homotopy, any two paths between the same 2 points are path homotopic. I proved that in previous videos. So what that means is that the only homotopy equivalence class is the trivial one, or the identity one, or the constant map. And so that means that this fundamental group at any point is trivial. The group with just the identity. All right, what is the fundamental group of, say, this circle? You can go ahead and look at Algebraic Topology 1.2. You can see my intuition set up, where I basically explain how this is equal to the integers. This is because you can take loops around the circle that are not homotopic to the identity. And every time you repeat that loop, that represents a brand new homotopy class. So you just get all the integers in those loops. And whenever you concatenate them, it's like adding integers. And in a similar way, the fundamental group of the torus at any point is just the integers direct sum with the integers. And you can go ahead and look at Algebraic Topology 1.2 to see why. So that's really cool. This fundamental group seems like a neat thing. But why exactly should I care about it? Because this kind of seems like sort of cool. Like you take a topological space and you can create a group out of it. Well, why is it useful? Well, it is useful because it actually relates all of these structures that we've been dealing with to just algebraic properties. So for example, paths can be viewed just as group isomorphisms. And it's going to be called the induced isomorphism. So what I mean by this is that I can take any path, alpha, which goes between, say, x0 and x1, and I can induce an isomorphism, alpha hat, which takes you from the fundamental group on x at your start point and brings you into your fundamental group at x at your end point. How do I define this? Well, alpha hat of some equivalence class, f, and the way we define it is by conjugation. So we will do the equivalence class on alpha bar, and the bar is actually important there, star, equivalence class on f, star, the equivalence class on alpha. So alpha bar flips it, so it goes from x1 to x0. F goes from x0 to x0 because it's a loop, and then alpha takes you from x0 to x1. And so overall, we go from x1 to x1, and then we get a loop starting and ending at x1. So how do I know that this alpha hat is an isomorphism, like I say it is? Well, first of all, we have to prove that it is a homomorphism. So how do I prove that alpha hat of f star g is the same as alpha hat of f star alpha hat of g? Well, let's go ahead and do this calculation all the way out. So alpha hat of f star g is going to be equal to, well, by the definition that we have alpha bar star f star g and then star just alpha. Now what I'm going to do is I'm going to insert the identity into the middle of this, like I did in the previous video. So instead of just writing this out again, in between the f and the g, I'm going to write something equivalent to the identity. I'm going to write alpha star alpha bar. That is alpha times its inverse, and right there is just the identity. And so that does not affect the end value of this whole thing. Oh, but look at that. We have alpha bar star f star alpha, and then alpha bar star g star alpha, which is then... And thus we have proved that it is a homomorphism. But why exactly is it an isomorphism? Well, because I can find an inverse for it. a two-sided inverse for it, namely alpha bar hat. Let's go ahead and very quickly check it one way. Alpha bar hat of f is going to be equal to, well, this is going to be alpha bar hat of, right there is, by definition, alpha bar star f star alpha, which is equal to, by definition, we're going to have alpha bar bar, which by the previous video I showed is just alpha. And then we star that with what was inside that we plugged in.
It's alpha bar, star f, star alpha.
And then at the other end, we just do alpha bar. And then you can clearly see we have alpha times alpha bar, alpha times alpha bar. We just get f out the other end, and thus we have the identity. You can go ahead and very easily check that this goes the other way around as well. All right, now something else you should notice about this is that if I have alpha, which say goes from x0 to x1, and I have some beta that goes from x1 to x2, what is the value of alpha star beta hat? Well, let's go ahead and apply this to some function f. This is equal to, by definition, alpha star beta bar, its equivalence class, star f star equivalence class of alpha star beta. So what is this going to be equal to? Well, we know that by properties of inverses, that alpha star beta quantity bar is the same as beta bar star alpha bar. Now why is that? Well, say we have xy, and we wanted to invert it. Well, first I would multiply it by y inverse to get rid of that y, and then I would multiply it by x inverse to get rid of the x. And so that tells you that xy inverse is equal to y inverse x inverse. So when you take the inverse, you flip the order of the operation. And so we get beta bar times alpha bar. Now by properties of the equivalence class, I can just write them as their own separate equivalence classes. And then we star f star, and then right there I can separate those into their own equivalence classes. On the inside, you can go ahead and see that that's clearly alpha hat of f. And then on the outside, we see a beta inverse and a beta. So that means we just conjugated this, which means that's beta hat of alpha hat of f, which means that really alpha star beta hat is just beta hat composed alpha hat. When you induce the isomorphism on concatenation, you just get their composition in the opposite order. Now the fact that we have these isomorphisms tells us a really interesting property. Namely, that if we have a path between 2 points, their fundamental groups are isomorphic. That basically means that if there exists a path between 2 points, they have equivalent fundamental groups. And so that's really interesting. That means that if we have a space where you can connect any 2 points via a path, that space would be called path connected, then all of their fundamental groups are the same regardless of the base point. And so this brings about a definition of a concept that basically says all of these fundamental groups are equivalent and they're all equal to some value. And this is the idea of a simply connected space. A simply connected space is a path-connected space, meaning you can connect any 2 points via a path, where the fundamental group of x at any base point is trivial. So, for example, Rn is a simply connected space. And so the idea here is that with a path-connected space, all of the fundamental groups are equal to each other, and we basically just say what those fundamental groups are. And so it's simply connected when all of its fundamental groups are 0. So I just said that Rn is an example, but what is another example? Well, the sphere, S2. Let's go ahead and see why that is. Let's go ahead and say you have your sphere. Let's go ahead and pick your base point, x0. Any loop around x0, no matter how you pick it, can always just be moved back in to the constant map. Right here, the one I just drew, you can go ahead and see how by the line homotopy, you can just move all of those bits of the loop back down to its base point. Even if you were to take a great sphere, which is the one that goes all the way around, you could just maneuver that bit from the back around to create a loop like that. And then right there you can clearly see that you can retract it down. And so this concept is important for Poincaré's lemma, or Poincaré's theorem, which basically says all simply connected three-dimensional manifolds, compact three manifolds, are homeomorphic to S3. And so it's very important that these spheres are, in fact, simply connected because of something like Poincaré's theorem. Now, something interesting about simply connected spaces is that they literally have not only trivial fundamental groups, but also trivial every path. Every path is homotopic to every other path in a simply connected space, which is what we saw in Rn. So a proposition is that given any two paths alpha and beta, which are between the same 2 points, they are homotopic in a simply connected space. So how do I prove that? Well, it's actually really easy, and I'm just going to draw out how you can prove it. So right here we have x0, right here we have x1, right there we have alpha, there we have beta. How do I prove that these two are homotopic? Well, I take beta bar, which means I flip the direction of this, so it's going that way instead. And then I can create a loop. I can do alpha star beta bar. And then I get a loop at x0. I go along alpha, and then I go back along beta. And so this loop is thus homotopic to the trivial loop, the constant map. What this tells you is that their equivalence classes are the same. So what I can do here is multiply both sides by beta. So I have alpha star beta bar, and then I star both sides by the equivalence class on beta. Right there, that's the identity. Right there we have beta with its inverse, and then we just get alpha equals beta. Their equivalence classes are equal to each other. And so they are homotopic. And that's that. All right. Now we can look at even more induced structures. For instance, we can do an induced homomorphism. So what an induced homomorphism is, we can take any map, H, any continuous map that goes between two topological spaces, and we can induce a homomorphism, which I'll call H at x0 star. The star is going to be on the bottom, and it's going to be between pi1 of x at the specified base point and pi1 of y at h of that base point. So basically meaning you map the base point into the other one. So that h maps x0 to h of x0. So the base points are analogous. And how do I define this? Well, I'll say that h x0 star of some equivalence class f, some loop, will just be H composed F, that equivalence class. Because remember, F as a loop can be viewed as a map from S1 into X, and H a map from X into Y. And so when you compose them, when you do H composed F, you get a map from S1 into Y, and that's a loop. And because F has a base point at x0, that means H composed F will have a base point at H of x0. And so everything works out. I am not going to prove that this one is a homomorphism because it's super easy. It's very similar to how I did that one. And it just uses the properties that I introduced last time. But what you should realize is that if I do, say, a composition, K composed H, at some base point x0, star, that is going to be equal to K at the base point H of x0, star, composed H at the base point x0, star. Now this is also pretty easy to prove. It just uses properties we detailed in previous videos. But what it does tell us is actually very deep. It tells us that this induced homomorphism is functoral. It tells us that if you compose first, then induce it, that's the same as if you induce them first and then compose them. This is a functoral property. What this tells you is that this fundamental group takes in a topological space with an additional point, a base point, and it outputs a group. But it doesn't just take in a topological space and output a group. It can also take in the maps, the morphisms between two topological spaces and induce a morphism between groups. So it takes the continuous maps between topological spaces and induces homomorphisms in groups. And this is something that preserves structure between these two different realms of math. That's a very cool connection to make. It's much more interesting than just having a group associated with the topological space. It's actually all of these properties related to structures in topology now being pooled into the realm of algebra. I recommend you watch category theory videos in order to understand this functoral idea a bit better. So let's very quickly do an example. The example is going to be of retractions. Now you might have heard about these before. What a retraction is it's a map, R, which takes you from a topological space into some subspace, A. And you do the subspace topology on A there. You also have the additional property that R of A is A for any A in that subspace. Basically meaning, if I have like the ball as X and this inner ball as A, all the things in A stay the same. All of those points don't move. All the points on X, though, move in towards A. So all of these points that are in X but not in A have to move in towards A. So a good example of this is the difference between a single line letter and the block letter that surrounds it. There is a retraction which takes you from this outer block letter in to that line, where you just move, where you keep this line letter, this thin letter, the same, you don't move it, and you move everything else around it into that single lined letter. So it's that connection between the block and the line letter. Now, something that's really interesting about retractions is that they're basically, in the algebra realm, surjections. So you would have, say, R at some point A0, and this A0 has to be in this subspace. We induce the homomorphism. But what you should realize is that any loop in A at that point is also a loop in X at that point. Because you have your space A, which is a subspace of the total space X. You have your point A0 in it. You have your loop F. If you just ignore the fact that it's in A, you get that it's a loop in X. And because this loop is entirely contained within A, that tells you that R composed F is just F. Because F is a loop entirely contained in A, and R is the identity on A. So what that should tell you is that for any loop that's in the codomain, the thing that maps onto it in the domain, via R A0 star, is just that same loop. And so this is a surjective homomorphism between the two. Sometimes this is going to be an isomorphism, sometimes, most times, it's not going to be. So, we learned about the loop space, the fundamental group, induced isomorphisms from paths, induced homomorphisms from functions, continuous functions, and simply connected spaces. We also learned about retractions right there at the end. What you should take out of this is that this is a brilliant and deep connection between algebra and topology, which you might have thought were two distantly related fields. But now you can see that they're actually very connected, and that's the idea of algebraic topology. And that's it.